Hi guys, it's me, Aaliyah, and today we don't have Mike Aubrey, our regular host, so I'm going to say what he usually does. Good morning, good afternoon, and good evening, wherever you are in the world, and welcome to our webinar with Alta Devices VP Rich Capusta and Chris France, who will actually be our presenter for today. I'll have Rich go ahead and start a little bit about Alta Devices and what this grant opportunity is that the teams have available for them.
Sure. Thanks, Leah. So we are super excited to be working with this particular organization. And Alta Devices, if you guys don't know much about us, we are a solar cell company. We've been around for about 6.5 years now, and we do a thin film, very efficient solar material, which Chris is going to go over in a lot more detail. But what I wanted to just say is we're really excited to be able to sponsor a couple of teams for putting solar onto the UAVs themselves. Right now, we're pretty tight as far as material goes, but we can certainly support two teams for sure, and we might even be able to do more than that. So as you guys are putting together your I guess, submissions and your applications, if there's an opportunity to increase the endurance on that particular UAV platform, then just let Aaliyah know, and we will look at all those different requests for solar, and we will pick, the two that we feel are the sort of the most appropriate, and probably on a first come, first serve type basis. So we are definitely gearing up for being able to support lots of different UAVs in the future, and we're looking forward to working with whoever decides to take us up on the offer.
All right, well, thanks so much, Rich. Appreciate it. We're going to jump right into the presentation with Chris. Chris, you will have to do an introduction. Mike is usually really good at introductions. I'm not that great. So if you could
Okay,
just talk about it, that would be great.
no problem.
I'm going to drop off, so I'll be listening in, but I don't think I need to be on the panel anymore. So, Chris, it's all yours.
All right,
Thanks,
thanks,
Rich.
Rich.
Okay, is the presentation coming through? Okay.
Yes.
So my name is Chris France. I'm a product engineer and failure analysis engineer over at Alta Devices. I help work with our customers to find the best solar solutions for your needs. Alta is unique in our position of being high efficient, flexible solar materials, as Rich said, and so we're trying to get into a lot of interesting markets such as sensors, UAVs, automotive, and I'm going to talk to you today about integrating solar energy into UAVs. We're going to step through a practical example using one of the Asia Tech drones, the Cyclops E, and look at how much power we can get from that, what are some of the choices that we need to make along the way, and a little bit about solar background and what we can do. So, and then the second half of the presentation is going to be open for questions and answers. So anything you've got as far as what we're doing at Alta, what we can do to help integrate solar onto your products, to help, I will address any of those. So let's see. My background is I have a PhD in physics from UC Santa Cruz and have been working here at Alta Devices for 3 years in the back end of our product line and dealing with customer interfaces. So let's see. Shall we get started? Okay.
Yes, we shall.
Okay, so I think the first question that we have to worry about is, so this is our outline, the outline of our presentation I'm going to cover today. Sorry, just trying. Okay. So the outline of the presentation I'm going to cover today is why do we want to put solar, integrate solar onto UAVs? And then there's going to be a brief section on solar energy, how solar cells work, and a comparison of different solar technologies. Introduction into thin film gallium arsenide and Alta Devices. And then the bulk of the talk is going to be a step through a UAV example, which we're going to estimate the flight time gains, optimize the physical and electrical constraints, talk about how we actually integrate the solar into the wing physically, and then talk about how we integrate the solar into the electrical systems, and then a little talk about the robustness of solar materials. So wrap up, and we're going to conclude, and then there's additional resources at the end. So on the right, we've got a picture of Alta's kind of standard solar cell product, a small matrix. This product would be about 6 inches wide, 4 inches. And then down in the bottom here, this is actually a AeroVironment solar-powered Puma with Alta Devices wings. So that plane went with an endurance of about 9 hours, where before solar, we had about 2 to 3 hours. So why do we want to put solar on UAVs? So there really is just one reason that we want to do this, and that's better endurance. So the longer time in the air enables a larger mission range and new use cases. And so you can fly farther from the operator if your regulations will permit it. You can get more contiguous imagery without having to stop, replace batteries, or return one UAV and replace another one. You can monitor whatever you choose to monitor for a longer amount of time. And you could do persistent search or communication. So by being able to be in the air longer, it just changes your mission parameters by a lot. So longer mission time also equals lower costs. We know that landing for many UAVs is one of the more dangerous times for damage. So if you have less landing for refills, you have less chance of damage. You also can potentially need to have a smaller fleets to accomplish the same tasks. So by being able to be in the air longer, you have to buy less planes, and that can also have a really good cost benefit. You can also use the solar if your aerodynamics work right. You can say, forget the range, let's just generate more power. So you can increase your payloads with the additional amount of power. So that is another option. And then, of course, the dream for all electronically powered unmanned or manned aerial vehicles would be to be able to be persistent flight. So if we could generate enough power during the day and have batteries that could run during the night, you could have a UAV up indefinitely. So I think we could be close to that depending on the plane, but I think we need a little movement in batteries. So the UAV I showed on the first slide is kind of what we're calling our small unmanned aerial system benchmark, and it's carried out by AeroVironment. So they achieved about a 3x increase in flight time for an additional 4.5 ounces of weight in solar material. So it's powered by our standard gallium arsenide cells, approximately 25% efficient, and there was 125 watts of solar installed on the plane. So it's an exciting opportunity, and we've delivered material to for other UAVs, and we think there's a lot of opportunity still waiting for us. So into the basics of our quick discussion into how solar energy works. So a solar cell is also called a photovoltaic. Photovoltaic breaks down as in photon, light, voltaic, electricity. So a photon comes in from the sun, is absorbed by the solar cell, and excites an electron. That electron is then moved out of the solar cell by moving to the conduction band, and the electron is connected as electricity, which can do work, powering your motor, recharging your batteries. So the material properties are very, very important based on what your solar material choice is. So the specific materials for your solar are going to determine the amount of light absorbed, the voltage produced by the solar cell, and the energy lost at high temperature. Because as all solar cells heat up, they will lose a certain amount of energy, not perform as well as they do in the lab. The material can be flexible or can be rigid, and certain materials are more sensitive to moisture, ultraviolet radiation, heat, light, and other environmental factors. So one of the key parameters of a material, and this is a little deep into the science, so we're gonna try to keep it quick and start off with an analogy, is the band gap. So solar materials have different band gaps, and that is one of the primary things that'll determine how well it'll work as a solar material. And the easiest analogy, to keep it simple, is think of water in a reservoir. so in a dam. And the water that's at the bottom of the reservoir is like your IR light in this analogy, and the water at the top is like your ultraviolet light. So if you have a low band gap semiconductor, would be akin to a hole in your dam that you use to collect the water that's low. So a low band gap, you're going to get a small amount of energy in the water, but you've got a very large volume of water available. So that translates into a solar cell, a low band gap semiconductor. You're going to get a low voltage, but you're going to absorb all the light. A good example of that is silicon. A high band gap semiconductor, you only get to collect the light or the water that's of high energy, but everything you collect is going to have a lot of energy in our water analogy and in the solar cell. So translating that, I apologize for the notifications if other people are seeing them. Translating that into what that means for solar material is that you're going to have 3 different types of solar materials. You're going to have a low band gap material, which is what silicon is, the most common solar cell material. And it has a low voltage but gets a high current. A medium band gap photovoltaic is kind of the optimum balance of absorption and voltage. And that's represented by the graph over here, which as your band gap gets larger, you see your peak efficiency peaks right in the middle, where cadmium telluride and gallium arsenide and copper sulfide are. And that is the material we work with, is gallium arsenide. Medium band gap semiconductors also match indoor lighting, not a big deal for UAVs, but it is also a neat note. And then high band gap semiconductors out here like cad sulfide are in general only used in the very expensive multi-junction cells where you have different material absorbing different light. So that explains, so that's one of the key metrics in comparing solar material. When you look at all the available material on the market, you've got a range, a spectrum of efficiencies. Now, I think the easiest thing to do is start off thinking about what do we need for a UAV. In the UAV application, we're going to need highly efficient solar energy because we have a very limited surface area. We have the wings, we can't even use all the wings, and so we need to get as much power out of the sun as we can. And we need a flexible material that can easily be integrated into the wing. We know there are examples of using rigid material in larger UAVs, but it is definitely a challenge. And also, less flexible material tends to be heavier. So we also need this lightweight material so that we can maintain our payload capacity. So we'll find all the material available has its limitations. The organic material and amorphous silicon, which are really good indoor lighting, are low efficiency. So 10 to 13% efficient, which is not going to provide much power gain for a UAV. A common thin film material that can be made flexible is CIGS. It is still only 16% efficient, and it is sensitive to moisture. Might not be an issue for UAVs, but CIGS has a potential for low cost. That low cost has not really been realized, with many of the CIGS companies having trouble. Then we come up into our mid-range efficiency, but we're starting to get into more rigid solar material. So the bulk of your higher or mid-range efficiency material is all rigid. And then gallium arsenide sits higher than silicon, which is our industry standard, up around 29% or 28.8% efficient is our record. It is flexible. It is 1 watt per gram, good temperature coefficients, and it has been well established for years in a non-flexible format in the space environment. So it is, we think, the best option for UAVs because it hits all 3 of the application requirements for this. So I'd like to talk a little about the flexible thin gallium arsenide films that we make here at Alta Devices. And so to start off, we'll talk a little more about the gallium arsenide solar material. The pros is that it has been an industry standard in single and multi-junction space qualified solar for years. There's tons of it floating around outside of the planet. It is robust to moisture, radiation, ultraviolet light. It is the highest efficiency single junction technology, and it has a really good temperature coefficient. You lose less energy when you operate it in the real world instead of the lab. And it is perfectly matched as far as our band gap discussion for collecting light at the surface of the Earth. The biggest disadvantages and why gallium arsenide, despite its penetration in the space industry and in concentrated farms and other places, is that the biggest con is its cost. Gallium arsenide wafers are 200 times more expensive than silicon wafers. They're also rigid. They're a single wafer technology, which means that they're very pure. They don't suffer from a lot of defect problems, but they're very heavy. And here is a picture of gallium arsenide installed on a neutron detecting satellite, the MidStar 1. So you can see many satellites are just covered in the material. So Alta Devices gallium arsenide technology is called AnyLight power technology. We are the leader in thin film gallium arsenide, and our goal as a company has been to bring the efficiency of gallium arsenide to a broad market. The technique we use has 3 important factors. One, we developed the highest throughput gallium arsenide MOCVD reactor in the world. Our reactor designs are patented. We work with industry leaders in tool development and can make material that is suitable for solar quality at a significantly faster rate than any other gallium arsenide reactor. We have to grow the reactor on these very expensive gallium arsenide wafers, but we transfer the solar film from the wafer template to a flexible lightweight carrier that's pictured below. And that way we reuse the wafer for growth. The wafer gives us really clean, high efficiency material, but the thin flexible carrier that we put it on allows us to be lightweight and go on flexible products. There's an additional advantage of this, that by making our gallium arsenide film layer thicker, we actually get a performance advantage over the traditional gallium arsenide. So there's light trapping that occurs when you have a very thin absorber film. Somewhat counterintuitive, but it gives us the world record efficiency of 28.8%. And then we have a matrixing system and a product size that allows us to develop flexible products to fit a broad customer base. If a customer wants a 1-inch by 2-inch solar solution, we have that. If a customer wants a 1 meter by 1.6 meter solar solution, we can build that too. All out of the same material, all out of the same tools. So where can we fit this unique technology? And we like to believe that we can fit our unique technology almost anywhere. It's going to depend, A, on cost, time frame, and scale, but we're working in a broad number of markets, including consumer devices, UAVs, automotive, incorporating into sunroofs and other glass parts to help with the electrification of automotive. Remote power, both for commercial, consumer, and for military purposes. And what is referred to a really interesting topic right now, the Internet of Things, where people hope to be putting sensors all around factory floors, putting sensors in your house, similar to the Nest thermostat, and running power to all these sensors adds a lot to the cost, requires planning. If you want to add sensors to a building or a vehicle or something afterwards, if you can just scavenge light from the rooms or scavenge light from the sun to power your devices, it opens up a lot of opportunities. So we're doing a lot of work in these 5 key areas, and we're learning every day as we go and trying to work with partners to figure out what the best fits are and to help out as many people power the devices that they have. So I'm now going to step into our example of our UAV. So our UAV example that we chose to use was the Asia Tech drone Cyclops E. I was informed that a handful of teams may be using this drone. It is pretty readily available, and it is a drone. It is a UAV that is designed to be high endurance. So, in general, which UAVs are best for solar? So, a fixed wing UAV is the best, is the most gains from solar integration. And that's because they have a large surface area and they require less power than rotor type UAVs to remain airborne. They tend to be the more longer endurance to begin with, and that's the best starting place. Now, there's many wing sizes that can provide useful power. I've got 3 examples. These examples are general examples that are actually on our website. A standard, a simple square type drone where both wings, then this is half of the wing of a more, what you would think of a more traditional airplane, slightly swept wings. And then a very common configuration, the delta wing style UAV, where if the fuselage is flat enough, it doesn't have to be perfectly flat, you could in theory pack solar over almost every top surface of the UAV. There's a lot of factors that need to be considered when planning adding solar to a UAV. The key is the battery voltage, because that'll determine the voltage of the solar panels we need. The use conditions, the payload, the available wing area, and what is the goal that you're trying to achieve. You know, if doubling your flight time would give you a significant advantage over competitors, if quadrupling your flight time, if increasing payload, you need to think of what your goal is trying to be and then tailor the solar solution to that. And our product engineering staff can help you optimize a solar design to your specific UAV, whether you're a manufacturer or you're an end user. So a little about the Cyclops E. It is the key factors is a 2.75 meter wingspan, high efficiency fixed wing airframe. The Cyclops E uses EPO foam. There is a slightly longer wingspan, Cyclops C, which is a composite wing. Both could take a solar solution. It's some various specs that may be of more interest. There's construction. Now, there's a lot of, the airframe is fairly basic, and I've seen a lot of solutions with looking on the web as far as battery, motor solutions. For our reference design, I've chosen a 6 series 5.5 amp hour LiPo battery. Seen solutions with 4 series. That's going to potentially change the solar panels we would put on there. So depending on what electrical options you're using, we could tailor something differently. And from the specs, it seemed a typical configuration would be after the batteries, you'd have about 3 pounds of payload that you could use for cameras and any other telemetry equipment. So the Asia Tech Drones is a sponsor of the Wildlife Challenge, or the Wildlife Conservation UAV Challenge, and that was one reason we picked that. And we think that this is a UAV that could easily be integrated with solar. So the first step in any solar integration of a product is going to be to collect the required information from the customer. That required information to do a basic layout is a dimensioned top-down schematic. We need to know the holdout areas. Those are areas with high curvature, such as the fuselage, movable and detachable parts, such as flaps and ailerons, and then also have to think about wiring difficulties. There is always the potential to use the horizontal surface of the tail section, but that also adds additional wiring that you would not have to do with just wings only. We need to understand the battery voltage. We need to understand the battery capacity, and to estimate flight time improvements, we need to know about what the consumption rate is, or we can estimate based on flight time and make some additional approximations. So the usable solar area is going to be mostly flat horizontal surfaces. I have to try to avoid shading and must be able to route the wiring back. So for the Cyclops E, the assumptions used is that we have a large wing area for cells That's highlighted in the green. There are some optional areas we could actually use. The flaps appear to be big enough, the control surfaces appear to be big enough that you could actually put a strip of solar on those, on the wings. And you've got a fairly large V-shaped tail. So solar could be placed on that. Because it's V-shaped, we actually probably have less considerations to worry about shading than we do when we have a normal with some T-shaped tails. And like I said in the previous slide, we're using the assumption that we have about a 25.8 voltage system when fully charged, be about 18 volts when discharged. And the numbers I was given to by John over at Asia Tech was that there's about 1.5 amp to 3 amp current draw when cruising based on load and wind speed and other conditions, and about a 10 to 15 amp draw on takeoff. So I'm going to assume a 2 amp draw for our configuration while we're cruising and 15 amps on takeoff. So we ran through 3 different designs here using only the wing sections. What we're calling a conservative, an aggressive, and the aggressive with some additional solar on the flaps. Those end up being a rated power of 41, 51, and 61 watts. The string length, so due to the voltage constraints, we chose 26 cell string as our base unit, which is like this 10.2 watt panel on the wing. This smaller panel here is actually 3 small strings that would then be added up to be 26 strings, or 26 cells. So this should allow us to have the right voltage to charge the batteries in conditions the batteries are at. You're going to get less than optimal charging when the batteries are fully charged, but as soon as the voltage drops slightly, you're going to be right where the solar really likes to operate, and you'll be generating really good power all the way down to the discharge voltage.
Your birthday or Kristen's birthday?
So we're trying to fit the maximum number of panels on the surface to maximize power. And depending on how you design your system, if you're putting protection diodes, something I'll talk about later, in the wings, you need to make room for that. And then also certain types of lamination methods, you need to have additional area. And that was one of the reasons that actually I'm going to go with the conservative layout for the rest of the talk. The aggressive layout I think we can do, but it would be nice to learn more about the UAV and actually maybe have it physically in hand before feeling really confident about that. So the result from the detailed layout and design is that we get the size and number of matrices, which would correlate with the cost, a diode installation and wiring plan, and then think of a lamination method that would work with the customer's integration. So for the Cyclops E, the conservative 41 watt design, comes down to, we can look over here, here's the build of materials for that, which would be 2 26 by 2 matrices, which generate about 10 watts, 2 26 by 1s that generate 5.1 watts each, and 2 26 by 1 that generate about 5.1 each, but these are the ones that are actually split into 3 parts. So our total power would be about 40.8 watts. And then the voltages we would get is what we call the open circuit voltage, which is the maximum voltage the solar would achieve is 27. And then the max power voltage points is right around 23.6. And that is assuming a blocking diode, which is something I'll talk about later. And then we need to put in 2 bypass diodes, another thing we'll talk about on later slides in more detail. But the interesting thing is what is going to be our projected range extension. So using our estimate of a 2 amp cruise, if we have about a 2-hour flight time from what's been communicated to me, that would use about 4 amp hours of the 5.5 amp hour capacity of the battery. So that gives us an additional 1.5 amp hour remaining for takeoff and climb, which at about a 15 amp draw, that's about 6 minutes of climbing, which seemed like a very reasonable estimate for me. Now, of course, the users who are more familiar with UAVs could potentially help us find better estimates for power draw when we're coming up with these designs. And the more information we get from you guys, the better we can come up with the right solution. So this solar array, if we just look at current and assume that the voltage is going to be limited by what the battery is doing, but the solar array would produce about an amp over an amp, 1.5 amp of current. It's actually rated for 1.65 amps approximately. So picking relatively conservative numbers of saying an amp and a half means that we would take our cruising consumption of 2 amps and it would drop that cruising consumption down to about half an amp of draw from the battery. Now, with that 4 amp hours of battery capacity, and we divide that by the half an amp, you get about an 8-hour cruising time. So we've gone from a 2-hour operation time to 8 hours by adding solar to this solution. Now, at 2.5 amp draw and the full battery potential, we see that's about 50 watts of power. If we go back to the previous slide, we see that both the more aggressive solutions without even using tail both generate over 50 watts of power. And so that means that with the right electronics, in the right conditions, we could probably have sustained flight with that type of, with a larger, slightly more aggressive system. So that would allow us basically to run on the solar during the day and really only use the battery time for when the sun is low in the sky or at nighttime, which is an exciting possibility. So to talk about integration methods are one of the next big things to consider. There's a lot of integration methods when we work with a UAV manufacturer, especially with composite wings. For end users who are getting your wings out of a box or pre-assembled, there's definitely less options. So I'll quickly go over what we can do when we're dealing with composite wings with the manufacturer. And the first thought is, well, you just take the solar matrix and you embed it in the surface, which we consider a pretty high-risk solution. The cells are exposed. They're likely to get damaged when you integrate if you're not familiar with handling the material, and so it's not recommended. Another thing we have tried is to directly embed below a clear fiberglass sheet if you've got a fiberglass composite wings. The disadvantages we found is that often the epoxy that you put behind the solar cell can squeeze between the cracks, shading part of the solar material. And also that fiberglass sheet you're using to protect the solar material is not designed to be optically transmissive. And so you're going to lose more power than if you used a solar front sheet. And then because you're handling bare matrices when integrating, you have to have more care and damage as possible. And the other thing is you're not really getting a weight advantage by using the fiberglass material, because a lot of our solar materials are just as lightweight or almost as lightweight. So our method of choice is to use a front side laminate where we use solar film, industry standard solar film on the front of the matrix. That would be shipped to you like that, so the front of the solar sheet is protected from minor damage while handling. You then lay that up in your composite mold and then build the wing on top of it. And we've had really great solution from aesthetics. You have no surface features that are going to affect your aerodynamics, and you're going to produce really good power because you've got great optical transmission. So for customers and for foam wing manufacturers, the best integration method is actually using that same front sight laminate, but we've had good experience with using a commercial spray adhesive to adhere to the top surface of your wing. Now, of course, there's other options that are available. We have not explored many with other customers, but there's a lot of things I could picture using clamps and other types of attachment mechanisms, but and we're more than willing to learn, which is a really exciting thing about our time here at Alta. One thing I didn't highlight from above is that we actually are working with solar front sheet manufacturers to develop and push the envelopes of what the industry can do. So we believe to be the thinnest, lightest front side laminate of solar grade material. It's been custom designed for us by a domestic manufacturer, and right now we have quite a bit of the material that we can use, and that is the material we would recommend for either integrating in the wing or adhering to the top surface. So there's electrical integration considerations that we also need to worry about. Wiring is one issue. You need to choose the appropriate wiring for your current loads. We can definitely help with that. If you're wiring on the top surface of the wing, you want to choose the smallest, thinnest wire to interfere with your aerodynamics as possible. Ideally, it would be great to run the wire inside the molds, gives you better protection, and allows you to use larger gauge wire so you're not having electrical losses. If you have detachable wings, you need to think about how they break away. How much do you need to reconnect them? You need to choose the proper connectors that meet those specifications. And then the biggest thing that we can help with our expertise is diodes in the solar panel. So there's something called a blocking diode, which is necessary if you think if you hook your battery up to the solar and then shade the solar completely, the battery will actually discharge through the solar panel. It'll cause the solar panel to heat up, and you'll lose your battery capacity. But by putting one blocking diode in, you prevent this. Now, the blocking diode ends up costing you 0.7 of a volt, and in that layout, that corresponds to about a 3% of the available power of the solar. So people like to try to get away from blocking diodes, but a lot of care would have to be taken to get away from blocking diodes. But if you're really looking for the highest efficiency solution, and you're willing to put in relays and stuff to disconnect the solar in cases where you might have battery draw problems, then you can bypass that 0.7 of a volt loss. Now, a bypass diode does not cost any power. It's not lossy. Put in parallel to the solar panels, and it allows a place for current to travel when the solar panels become partially shaded. For our technology, we recommend one blocking diode per about 13 cells in series, and that does not have to be on every panel. You can do it on a couple panels. For this solar design, there's a couple strings that have a lot of space next to them. We could embed the blocking diodes there in the wing with ribbons, or you can actually put them in it near the battery where you make the electrical connections. So here on the left, we have a table talking about the pros and cons of that. So if you put the diodes in the solar panels, it's easier for the customers because we put them in, they've been laminated, they're protected, but it takes a little bit of space away from the wing. Oftentimes that space is not space where we could have put solar, so that's not usually a big deal. But it also means there's less wires to be routed back to the battery. I could go into those details, but yeah, for this it would be one less wire. Now, if the customers wire the diodes at the battery, it's going to be less expensive for the customer because we're not actually doing the wiring. It maximizes the solar energy on the wing. Sometimes that's not the case because it was energy we couldn't put area we couldn't put solar cells on. But it does require more wires to be routed to the battery. That's a clear difference between the two. And we're not currently an electrical power management company, but we're doing a lot of work partnering with electrical companies that make power management chips, solutions, work with microcontrollers for power management, and we're working on trying to develop reference designs that we can give to customers. Currently, a lot of those solutions tend to be in portable electronics and sensor voltage ranges in and around the 3 to 5 volt voltage range, and we haven't worked very extensively in the range that UAV voltages are, which tend to be 10 to 30 volts. But there's a lot of solutions, from the simplest solution for power management at the top to more complicated and more expensive. The trade-offs tend to be that the more complicated it gets, the higher efficiency you get, but it means more components that you have to put in, which means slight increase in weight, or a lot of increase in weight if it's done wrong, and more cost, which is potentially not the biggest issue for UAVs, and you know, it does just get more complexity. So the first simplest solution that people tend to go towards is just hook the solar panels up to your battery. And going back to the previous slide, we really don't recommend that unless you want to keep things as simple as possible and we want to really plan that solution out. So the next best solution would be to put a blocking diode in. Now, the efficiency is going to vary a bit depending on conditions, but for the most part, if you're operating in partly cloudy conditions to full sun, mostly during midday, you're going to get a really consistent voltage with our technology, which means you're going to get a really consistent efficiency, and we can design our solution to match your batteries really well. This is our most common solution for UAVs, especially for a first engagement. There's what's considered a one-sided voltage regulator, where you're allowing the solar panel voltage to be dissimilar from your battery voltage, and then you have a regulator that provides some proportionality and tries to match your battery voltage as good as possible. A chop type algorithm where you're just using a simple voltage divider. If you have a good voltage match, it provides minimum losses. If your voltage match isn't, if your panel voltage is significantly higher than your battery voltage, then you're going to lose a lot of power. Then there's more active solutions, which is in a buck and a boost mold, where your solar panel voltage is greater than battery or less than. Those can be pretty efficient. And then there are a more expensive single-sided operator where you try to get your voltage right near where your panel voltage is, and the electronics can either boost or cut down on that voltage based on its operating mode. Then there is what I call a two-sided voltage regulator, where your voltage regulation is going to be take the panel voltage, go to an intermediate, and then go to your battery voltage based on the chart. And then that can either be a fixed battery voltage, or it can be related to what the charge conditions are of your battery. So if your battery wants to accept a full charge, you can go into a full charge mode. If it's fully charged, you can go into a trickle charge mode, and then also just power your electronics. And then there's what's called maximum power point tracking, which is the most advanced solar solution. So that allows, it will find what the best operating voltage is with your lighting conditions to operate the solar. Then it will then take that power, then translate it with either a buck or a boost controller to exactly what your battery needs. These solutions can be in excess of over 90 to 95% efficient in electronics. But they tend to be the most complicated, and if they're not designed specifically for your voltages, they tend not to be very compact. And that means that they add a lot of weight. But these are the solutions when you really want to get into a really solid integration. These solutions are available, and there's a lot of experience integrating these in the industry. So the last little bit I want to talk about is just the robustness of the solar material. The easiest thing to think of, so the material that we put on the front to protect the solar panels is a Teflon front sheet, which is similar to the material that you put on a Teflon coated frying pan. It punctures. It's not going to protect a lot of protection. Force is going to get transmitted into the solar material and could cause damage. But abrasions and other handling damage and simple shocks, it's going to provide a very good amount of protection. So now, if it is adhered to the wing skins, it's going to be slightly less robust because you have a potential for delamination. So we need to really think and plan that out as far as getting it adhered or glued down really well. The bypass diodes protect the solar when it's partially shaded or it's damaged. And then there's a little bit about our inherent cell reliability. So with correct encapsulations, like something you would see in a solar farm or on the roof of your house or your neighbor's house, our solar cells are capable of surviving the 25-year lifetime that the industry requires. Lightweight encapsulations like we've used on UAVs, we're pretty certain that we have a 10-year lifetime. And more likely the cause of any problems with your solar could be catastrophic damage during landing. We have survived successful wing detachment landings with the AeroVironment's plane and with various other UAVs. So we know it's doable. We have not had customers come back and go through hundreds or thousands of flights to tell us to get some good statistics on it. So we're robust enough to work. We know that. We want to explore that with our customers. So in our wrap-up, a real simple conclusion so we can get on to the questions is that we have a thin, flexible, high-efficient solar material that's ideally suited for UAVs at Alta Devices. Integrating solar on UAVs can give significant range increases on the order of multiple factors over their current range. And there are many options for integrating solar, and we can help you find the best solution that works for your application. There are additional resources. I don't know if this presentation is going to be distributed, but if it's capable, then there's going to be additional resources at the end. You can check out various websites, and I've got some references to some of the early stuff in the material. So
Okay, great. Thank you so much, Chris. One thing I do want to show, actually, if you could keep that page up, that would be fantastic, is one of
Yeah,
your
trying to get to it.
little solar cells. Can you guys see that?
Oh yes.
It's really, really thin.
Yeah. Can you try bending it a little?
Yeah, I could bend
Show
it
them.
right
Yeah.
now. Yeah, so when he says flexible, he definitely means flexible.
hmm So I've done a lot of the evaluation of the flexibility and damage points, and for certain encapsulations like the ones we use on UAV, we've gotten down to 1 centimeter radius of curvature and not seen significant damage. So
Yeah,
that is very, very, very tight bending
yeah.
radius.
So I think Mike's back. Mike,
Hey guys.
hey, we missed you earlier today.
I missed you guys. Chris, a great presentation.
Thank you.
A question for you. So it looks like the weight of these cells themselves, if that's truly the thickness of them, those are pretty negligible. Do you have an estimate of the weight of the systems that would be ideal to regulate the voltage? And how much, I guess, net added weight do you anticipate for
So
that setup you showed?
so for the simplest solution we recommend with a good voltage matching to your battery, and then a blocking diode and bypass diode, you're talking grams of weight. Not much. You've got a couple diode ribbons. The diodes are small electronic components. Each diode probably weighs maybe 1 or 2 paper clips.
Wow.
That is the simplest solution. As far as electronics go now, all the voltage regulations that I talked about, some of the more complicated systems and even some MPPT systems, are things that are in your cell phone. So that can give you an idea of how small these chips can be. I don't know what the smallest, lightest weight solutions are that are in the voltage and power range that we need for UAVs. But if they're not there, they can easily be developed. So you're talking still pretty small weight. But I don't want to give a specific amount for a larger solution. But it's not, the biggest thing I think you'd be dealing with is maybe a couple inductors that are, what would that be? Yeah, it's hard for me to estimate that, but you know,
Sounds like
a
you're
small
talking
inductor
grams,
would
not
be
kilograms.
potentially about the weight of 6 quarters.
6 quarters, yeah. Well, okay, so then you're in the realm of, I'm trying to debate, like, is the added weight, are we removing batteries? I mean, are we actually kind of swapping out batteries for replacement of this, kind of transferring electronics? Sounds like you've got a really nice weight in this system. That sounds awesome.
Yeah,
I'm really interested.
That I think is one of our
I did
best
not realize.
advantages. And you're right, the electronics can be offset by decreasing your battery if that's something you're okay with going towards. And yeah, but it's definitely very minimal.
Here, I got a couple of questions for you that came in from, let's start about with a question here from Michael Robbins. He's asking, you've mentioned single junction cells. Are there other types of cells that we should be considering?
Yeah, we actually have, we've developed a tandem cell, a dual junction cell. It's over 30% efficient. For a bit of time, it was the world record in the dual junction regime. And we can push harder and get back that record, we believe, but it just has not been a priority. The gains from multi-junction, for most customers, I think would not be particularly beneficial for the cost. So you can gain a couple percentage point of efficiencies by adding a second junction, but the complexity is up there. For really pushing the envelope, a dual junction or a triple junction cell could give you some good advantages, but that is, I think the number of customers that would be helpful for would be limited.
Sounds good. Toby had a question, kind of a statement. Well, I'll just go and read it. We'll let you respond. Have you explored hydrogen fuel store? I'll go ahead and paraphrase this question, actually. Well, I'll just read it. Chris, have you explored hydrogen fuel store? Has managed the power of the Aero Pack? I believe it operates like buck boost example, but I know that it is for UAVs. Do you have any just kind of general comments, I guess, in using that kind of technology?
It is not something we have worked with. I do not know of any case where we've really thought of integrating with hydrogen
Sure.
fuel cells yet.
Sure.
It's not something I could say we'd be opposed to, and if we wanted to take a discussion to offline so that I could learn a little more, then
So
that
I'll
would be
jump in. This is Rich Kapustotopin. Can you guys hear me?
okay.
So I know of one customer that was thinking about combining both the hydrogen fuel storage approach with solar cells, and their goal was to try and create a UAV that could fly 24 hours. So the solar cells would allow the plane to fly all day long, and then the hydrogen fuel cell would allow the plane to fly all night long. Now, you could then get another day's worth out of it on the second day, so you could probably get to about 36 hours, but then your hydrogen fuel storage would need to be replenished. So that one's not a renewable energy source, and there's no way to renew that with solar. But there is a possibility to marry the two technologies together and create something that can fly for possibly 2 or 2.5 days using the combination of the two technologies. No one's done it yet, but in theory that you should be able to do something like that.
Yep, looks like you answered it. Any other questions, guys?
Yeah, Mike, there are a few questions. I guess you can't see them. From Michael Smith.
Which I see some general comments. I don't see questions. Well, go ahead. If you're seeing ones, I'm not. Read on.
So it says, thanks. Can you estimate the total additional weight for the?
Yeah, we asked that one. So it's
Oh,
it's
oh
going to be
yeah,
in grams,
I
not
realized you already
kilograms.
asked that one. Yeah,
Yeah.
I think you already asked that one. Hold on. I think that was. Oh, you're right. I think that was it then.
The other thing Chris didn't mention, which I'll also add to that weight question, is some of our customers are actually laying the solar cells into their mold, so they're actually replacing wing mass with solar cell mass. So you're actually not even adding a significant amount of weight from the solar cells themselves, because it's becoming part of the wing structure, and the actual wing itself at the end of the day probably weighs what it used to for the most part, and then you're really just adding a little bit of weight in wiring and like you mentioned, the diodes and some of the electronics, which ultimately becomes almost negligible.
I got a durability question for you, Michael, or Chris, from Michael Robbins. Have you done? So you mentioned you've done testing in one plane for your radius of curvature. Have you done stuff where you've tested in two planes? I guess kind of a colloquial way to describe it is how much can you torque those things before they start damaging?
Yeah, we've done. I've 2-plane radius of curvature. No, have not done a significant amount of studying on that. I cannot picture that for the UAV environment, the forces in UAVs I can't picture being a problem.
Sure.
The biggest issue, you have more problems when you have repeated bending. That's where we have to really, really worry about it, and I mean large amounts of bending.
Mm-hmm.
So if you're permanently, once you mount it on the wing, it's going to stay in a fixed position, independent of what that wing is going to flex. That flex is probably very minimal perturbation, but no, it's not something we've really worked with in huge detail, partially because I think to put the effort into looking at that robustness, we really need to know what the end user customers want. So any feedback that could be provided on specific tests and specific constraints that you could see the material being subject to in your application is something really useful.
Okay.
So that's why the most we've done is some very generic single axis.
Cool. I got a question for you around maintenance. Did you cover just kind of how you would the expected maintenance on kind of cleaning the cells and such periodically? Is there?
I did not. I think it would effectively, it would be wipe it with a damp cloth,
Really?
maybe
Okay.
mild detergent.
So you don't have to use any like harsh acid solutions or anything to.
No. So the solar front sheet material can be available in two different formats. One is a glossy finish. The glossy finish does not collect nearly as much dust as the other finish, which is a matte finish. So for most UAV environments, a glossy finish is probably more ideal because the reason when you go to a matte finish is you're trying to get rid of that shiny glare, which can be a problem if basically you don't want your material to be seen. So if you're doing for certain customers in maybe surveillance applications, you don't care. But even in that place, the solar is normally facing upwards. So your gloss finish, it stays pretty clean. You wipe it down. The matte finish, it'll collect a little more dust, which just means it needs to be wiped a little more frequently.
Okay. So guys, I guess we have time kind of for one more question here before we're at the end of the hour. Cost.
Can I jump in real quick? There was one question about durability, and I just wanted to add another comment about the fact that we do have a customer with AeroVironment. You know, they're putting it on the Puma AE right now, and they've done a bunch of different tests for durability, and they're also about to go through a whole nother battery of tests. So, you know, as much as we can't necessarily share their data, we're pretty confident that our material can sustain, you know, some pretty rigid and rough environments out there. And so AeroVironment is certainly pleased with the results that they're seeing on their end with the integration that they've done on the Puma.
Awesome.
Thank
Yeah,
you,
it
Rich.
looks very durable. A question on cost. What would you estimate a setup for the Cyclops? How much do you think that would cost?
I'm gonna pass that on to Rich.
For something like a Cyclops, we're probably looking at, you know, on the order of $5,000 per plane.
Okay.
And that's for sort of initial volumes. We certainly expect that that's going to come down over time, and we have plans to scale our capacity, and you know that could even come down by an order of magnitude over the next couple of years. But if you wanted to go put that on a plane today, you're looking at about $5K per plane, and then there's some NRE and some design costs and things like that you know go into some of the initial development work that needs to get done. But that's kind of a rough idea of what we're looking at.
Most of the cost is in the actual cells themselves.
Yeah, definitely. Yeah.
Okay. All right, guys. Princess Lee, am I missing anything obvious in that question list that we need to cover?
No, to add on what Rich says about cost, to understand we're actually we have a fully functioning pilot line here in Sunnyvale, California. So all the material comes out of this line. The plans in the future will be the larger manufacturing line, and that will definitely bring costs down. So yeah, the material costs are because we're just coming out of R&D mode and ramping a line.
But on a good note,
My editorial comment, what you guys are doing on the weight is exceptional. I can't believe how light those things are. And I look at these things, I think of the solar panels on the roof of houses and such, and I was thinking, oh, you're throwing this like big chunk of like aluminum framing on top of an UAV, and you're talking about it's something that's the equivalent of like a sticker.
Yeah,
that's incredible.
Right here, Mike. Did you saw me put it up, didn't you?
It's incredible.
Yeah, it is. I mean, it's really cool. I was like, wow, this is definitely worth putting on a UAV, and $5,000. I think it's still going to be worth it if you can get the use out of it as well. So, you know, yeah, it's $5,000, and we are so fortunate to have Alta Devices sponsor at least two of our teams, and perhaps maybe another one as we move into September timeframe. But at least two teams can qualify. So if you guys are really interested in getting some solar cells from Alta on your UAVs, please send me an email at director@wcuavc.com. And then that way, what we'll have to do is work with Chris and some of the other people at Alta Devices to see if it would actually make sense to have the solar cells on your UAV. And if it makes sense, then you would definitely be considered as one of the best options. So we use Cyclops because they are one of our sponsors. There are at least 6 teams or 5 teams that have the Cyclops C and 1 team in Australia that has the Cyclops E. So we have that option of being able to qualify one of the Cyclops teams because we've already kind of done our homework on that. So if you got a Cyclops, make sure you send an email that you're interested in getting some solar cells from Alta on that. So that's director@wcuavc.com. Mike, I don't know, do you see any more questions? It's kind of, I think Steve wants to know if we can get a copy of the presentation. Chris?
Yeah, I don't see a reason why I can't send it out.
And plus, it's going to be available on our YouTube channel as a webinar, recorded webinar. So it will be available. And if you guys are interested, I'll definitely send me an email if you would like it. I don't want to send it out unless you need it. I think that should be it. Do you see any other questions?
No, I'm just some accolades thanking you for the time.
Yeah.
That was super interesting. I didn't realize. Opened my eyes.
Did you ask the question from Shannon about direct to battery or direct to battery with diodes?
No. Let's do that question. So Shannon asked a question around in your direct to battery setup or direct to battery with diodes. Is there a risk of overcharging a battery? Like say the vehicle sits in the sun for a while before the flight.
Very good question. I think there is. Yeah, in a way, it depends on how you're matching your battery voltage. If, like in this situation, your fully charged battery would be at about 25.6 volts, and the battery, the solar panel actually really wants to operate below that. So at that 25.6 volts, we would have to look at the actual panels or do a little more modeling to see what the current that it would want to generate at that fully charged voltage is, and it might be low enough to only be to not be a danger, but yeah, it could definitely be an issue. Now, you can do a direct to battery with a charge regulator in there too, without worrying about the voltage matching, and that would basically work like a current cutoff switch. But yeah, I think there is a possibility if it's not designed quite right. But I think this design, you would be safe. But yeah, it's something we would have to pay attention to. Good question.
Yeah, thanks, Shannon. Well,
and thank you guys for the opportunity.
Yeah, Chris, thanks so much for presenting. This is really informative and interesting, and obviously very relevant. Thanks for taking the time to make it applicable for what we're doing.
Yeah, we really appreciate it. Thanks to Chris and Rich from Alta Devices for such a great webinar. We'll have it posted up, available hopefully by tomorrow. So any of you that are interested in watching it again, slowing it down, please feel free. If somebody needs to get a hold of you, Chris, is there an email contact information that you would be willing to share?
Yeah. I mean, I can share my email. We also have an email at the website, so you can go and send marketing requests, which I think pretty much go straight to Rich.
Okay. All right. Well.
So yeah, the email that I've got, you can distribute, and I can answer questions.
All right. So I will go ahead and send that out to the people that were on the webinar today, along with your presentation.
Okay. Yeah, I'll send that over to you in a few minutes.
Cool.
All right. Sounds good. Well, thank you so much.
Thank you.
All right, guys. I guess we'll see you on the next one. And
right.
Yeah, safe flying.
All right. Thanks, Mike.
Later,
All
guys.
right. You take care. Cheers.
Bye.